Hello and welcome to the second part of my presentation. This is going to be the self-curated portion of the project where I have came up with my own question. The first slide is the relevance of question to topic explained. So I'm going to read the question and then we'll go over it. A student is testing the force needed to stretch a spring. The student fixes one end of the spring to secure a wall and applies a horizontal force to the other end. The spring has a constant of 550 newtons per meter and an unstretched length of 20 centimeters. How much force is required to stretch the spring to a total length of 30 centimeters? So we have the constant, which is just the stiffness of the spring, and then we have it secured to a wall, and the student walks up and needs a horizontal force to stretch the string from its initial, which is 20 centimeters unstretched, and then to a required length of 30 centimeters, and we're going to need to figure out how much force that's going to take. Its relative, or excuse me, the relevance of the question is that it uses Hooke's law, which is F equals K times X, or X times K. You have your F is the force, you have your spring constant, which is notified as K, and then you have X, which is your change in displacement, or the initial from the original, or initial from the extended, excuse me. Okay, in this next slide, we have the motivation development. We're on the part that's part C, benefits of understanding the question given. So the understanding of Hooke's law, it helps in engineering, a couple other fields. Basically, you're testing elastic limit of stress and strain. The question itself it helps the student develop, critical thinking skills. It helps the students to solve other questions relating to elastic limits of stress and strain. And then Hooke's law is foundational in civil engineering. It's used for testing the limits of composite materials, so any type of steel, I-beams, piping systems. It's foundational for making sure that those materials are safe and have the required load limits that they can take, so that there's no deformation or buckling or any type of break within the structure that would cause a collapse and potentially harm people. So it ties into safety all around. Okay, in this next slide, we got the process of writing question outlined. So the process for me was first had to, find something similar using Hooke's law, which is basically just going back in our textbook and looking at our prior notes, because we covered this in one of our labs. And then essentially chose a question that was related to Hooke's law that I could formulate, and then make sure that the question was not too difficult, didn't have like 6 to 8 steps that would be really difficult to solve and make it harder on the students. Like we want to make sure that we make it easy enough that we can all solve the problems so that we can learn in the process, instead of making it so difficult that it deters you from wanting to proceed forward. Okay, so in this slide, this is the uniqueness of question discussed. You can apply this type of problem involving springs and elastic material to a number of different questions that you'll come across, and it'll be something similar. The question itself helps an abstract concept become more understandable or more tangible. It gives the student a deeper understanding by formulating the question, going through the process, learning what to put together and why. And then there's also, it engages the student with system mechanics, which is essentially it's engineering mechanics that deals with study of forces, motion, energy, materials. Then it combines it with system engineering, which is the process of planning, integrating, and managing complex systems. And it focuses on various components of system interaction to perform together and achieve the same functions. Okay, so in this part C, we have a relevant chart, graph, diagrams provided to explain the question. So over here, you can see like a graph that I basically had made up. On the x-axis is the extension in meters, and then the Newton force on top. And as you can see, or the y-axis, excuse me, is the force. So as you can see, once you pull per 0.1 meter, you get an increased force of newtons along the x and y axis, kind of in a linear pattern. So of course, as you pull on the spring, you're adding more force, which is represented here in the graph. Okay, so in this section we have the relevant formulas and the constants explained. So once again, like we talked about earlier, the formula for Hooke's law is force equals the constant or the stiffness times x, which is the displacement or the original length or, from the extended length, which is the displacement. And then we have the amount of force of the, or excuse me, the spring constant, which is the stiffness of the spring, which equals to 550 newtons per meter. You also have the displacement, like we talked about, which is the extension from the wall, basically with the question. And then you have the unstretched length, which is just the spring sitting at the wall horizontally. And then you have the total length, which is from the base stretch all the way out to 30 centimeters. All right, in this slide, we're talking about the solving process. So I'm going to go how the question breaks down, how to solve it step by step. So first we want to identify the values, which are, like we spoke about before, constant, which is 550 newtons per meter. And we'll see later, while the meters cancel out and just becomes newtons. We have the initial length, and then we have the 20 centimeters of the initial length, which we have to convert that into meters so that we can cancel out the meters from the constant. Then we have the 30 centimeters, which is the fully stretched out length. And then you have to convert that into meters as well. Again, so it'll cancel out the meters when we do the formula. And then we have the change in displacement. So you take your extended length and you subtract your initial length, and then that comes out to 0.10 meters. Then we have all of our values. So all we have to do is just solve. And then you have your force equals 550 newtons per meter times 0.10 meters, and that will give you, basically just move over the decimal one place and you get the force is equal to 55 newtons. So essentially what I had learned from this is that the distance that the spring was going to move was about the width of a hand, which is like 3.97 centimeters. And it would be the equivalent force or weight of a bowling ball, if you could think about it like that, would be the amount of force applied to pull. So it's a pretty stiff string, and you're probably going to need a pretty strong student, but it can be done. Okay, so in this slide we have the solution correct, applicable to topic, and the solution we did come up with by solving step by step through the process came out to be 55 newtons, and that was correct. You can verify by setting up the problem yourself and going back and checking, plugging your numbers to the formula, follow step by step like I've shown, and you should come out to the same answer. If you don't, I guess I failed, but that's okay. Like I said, the solution was verified step by step, so we went through that. And the question is in direct correlation with Hooke's law and how the spring constant works, how you find out your force using displacement and setting it up. So the problem overall effectively demonstrates the use of Hooke's law, which is basically the elastic limit. You get that linear line that you find comes to a point where it breaks or becomes deformation, and then past that point, Hooke's law starts to break down, and then I believe you have Young's modulus take over, or Young's modulus is related to Hooke's law. So, okay, so in this slide we have additional valuable information. So Hooke's law doesn't just deal with springs, it deals with any elastic material. Also, it's used within resonance and acoustics. It basically describes the amplitude of oscillations that grow inside of a system until the system can be no longer described by Hooke's law. It kind of comes to a break point. That can be an example of that can be distorted sound in certain types of rock music, which I'm sure you probably know. It's also Hooke's law, of course, like I said before, is foundational in material science because you need to understand the strength of a material by its stress and strain, and its compression. So your tensile strength within rebar, your compression strength within the concrete, that coming together, and then testing that to the point of failure can tell you how strong a column can be inside of a building or a concrete slab, or it has multiple slabs on top of a building with multiple concrete and steel beams, and all those things, have to be tested before they're put together, because if not, then you're going to have a building that can fall upon itself or, cause great devastation. Of course, like we talked about before, Hooke's law describes the elastic behavior of most all solid materials until its breaking point, and then anything that's like rubber or polymer, that's a non-Hookean material. So that has basically stretch and it comes back. So like I said, it breaks down past the elastic limit. So Hooke's law is fundamental for all kinds of material science and testing compressions and everything like that. But past a certain point, it has, no information that you can get out of it because it goes past a point and breaks. Okay, in this slide, it talks about the additional student interests described. For me particularly, this is going to be certainly interesting because I'm headed for my major in civil engineering, so Hooke's law is going to be well within those classes. It's going to be in a number of future classes, including statics, mechanics of materials, structural analysis. That's all going to be classes that I'm going to have to participate in that cover a wide range of material science. It's going to introduce any of the forces that cause deformation. It's going to talk about stress strain, axial loads, torsion, deflection. And then, the analysis part is really important factor in engineering to calculate deformation of beams, frames, and trusses. That's going to be a huge part of any type of civil engineering, is to be able to present an analysis that's backed by your data to show that this building can withstand this amount of load, or this bridge will not fall into the ocean. So I am excited to where that's going to take me. And it's just nice to have a project like this that gives you a little bit of a prerequisite into what's going to come next. Okay, so in this slide, this is the overall summary of topic presented. So overall, I really enjoyed making this presentation with my group. I think everyone did a really good job working together. We communicated well. We made sure to try to get ahead of it as best we can, even though people have separate lives. They're working, raising kids, going to school at the same time. So it makes it difficult for everybody to get together and communicate. Blackboard was pretty much essential in us communicating on our group messages. That's how we basically talked back and forth. And then we set up our video portion, as you know, in class and did it on the projector, which, thank you, that was extremely helpful. I think we all did a great part in working together. Everybody put in enough information to make good slides that represented the entire concept. I think they were really thorough in all those key aspects. And overall, I feel like it was a really good presentation, and I think everybody did their part. Okay, and one of the last parts is 6.4. It's relevant sources for all the information given. So I don't think we could have fitted everyone's sourcing on here. That would have not fit in the actual presentation, but for the slides that I presented and for the textbook that I used, because eventually ran out of pictures from certain sites that we would use for our information, our sourcing. I mean, some sites would just be completely no pictures whatsoever, diagrams, just information. So these are the sources. I made sure to put them in their actual web address instead of a link. And then I'm not sure if in the PDF form you're going to be able to click on it, but you should be able to at least highlight it and then check the sourcing to make sure that it coincides with information that's been given about the slides. And then, end of presentation. We did it. We made it happen. Big thanks to everybody involved. I think everybody did a great job. I'm looking forward to graduating and starting next semester over at Lamar University and finish my bachelor's degree in civil engineering. And then from there, I don't know, the world's an oyster. We'll see. All right, thank you.